Hello, are we ready?
Why are they up there?
Okay. Well, good afternoon, everyone. Are we started or just give one more minute? Okay. Good afternoon, everyone. I'm Dr. Rose Hu, the ECE department head. It is my great pleasure and honor to welcome today's seminar speaker, Professor Ted Rappaport, a true pioneer and a visionary in wireless communications. Professor Rappaport is currently the David Lee Ernst Weber Chair Professor of Electrical and Computer Engineering, Computer Science, Medicine at New York University, and the founding director of NYU Wireless. But for all of us at Virginia Tech here, this visit carries a very special meaning. Early in his career, Professor Rappaport founded two of the most influential wireless research centers in the world, one at UT Austin and one right here at Virginia Tech, the Mobile and Portable Radio Research Group, now known as Wireless at VT, co-directed by Professors Jeff Reed and Lingjia Liu. Both are also here in the room. Professor Rappaport's vision and leadership laid the solid foundation for Virginia Tech's worldwide reputation and recognitions in wireless research. So we all give big thanks to Dr. Rappaport's early work at Virginia Tech. And also among his very lots of groundbreaking contributions, Professor Rappaport pioneered radio propagation modeling, developed E911 emergency location system, and more profoundly led the adoption of millimeter wave and sub-terahertz spectrum for 5G technology now powers billions of devices worldwide. And Professor Rappaport is a member of National Academy of Engineering, a fellow of IEEE, AAAS, ACE, and a recipient of numerous prestigious awards recognizing his research, educational, and entrepreneurial impacts. So I could easily spend much longer celebrating Professor Rappaport's extraordinary contributions and achievements, but I know we are all eager to hear from him directly. So now let's welcome Professor Rappaport for his exciting talk on global spectrum usage for 6G. Thanks.
Thank you very much, Rose. And thanks to all of you for being here. I understand some of you have to be here for a class. So let me get some help from the IT people to make sure it shows without the things. But it's really a thrill for me to be back at Virginia Tech. Virginia Tech hired me 37 and a half years ago. They gave me my first job out of college. I graduated from Purdue in 1987, and I wanted to do wireless because my PhD, actually, I didn't know it at the time, but was a founding body of work that led to Wi-Fi. And I knew cellular would be big, but the only university in the country that was willing to hire a 26-year-old fresh out from Purdue was Virginia Tech. So thanks to the university, I've had a wonderful career. Wireless has been very good to me, and I've been able to be there from the very beginning. And I've had a great thrill of working with colleagues like Jeff Reed and Lingjia Rose. So many of you, it's been a wonderful journey. So it's fun for me to be here at Tech's newest building here in Alexandria. What an amazing space. I get asked to give talks fairly regularly. And in my career, I've always tried to do something new whenever I'm asked to give a talk. It's easy to give the same slides over and over again, but I've always tried to do something different. So today I'm going to do something I've never done in my career. I'm going to present to you work that I did this summer on 3 separate collaborations. And these are 3 journal papers that I was invited to write on 3 different topics that all focus on 6G. And all the work's pretty exciting. So the slides I'm going to present are actually in 3 papers that have either just published or are about to publish now. In fact, the papers are in a, how do I change the slide? Okay, thanks. They're all appearing in a new journal, a Nature partnership journal called Wireless Technology. I got a call around April or May of this year from Professor Alawini, Slim Alawini in the Middle East, very famous wireless professor. He said, I'm starting a new journal. It's a nature-related journal. I'd like you to write some invited papers. So this is the result of 3 collaborations in 3 different topics, all that I think are going to be important for the future of wireless. And this is the journal they're appearing in. I'm clicking the right arrow and it's not changing. So, oh, there we go. I'll click that area. So here's the first one, first of 3, spectrum. Now, Virginia Tech's historically been very powerful, a research leader in spectrum. And the software-defined radio, Professor Reed, CDMA in the early days with Brian Warner, and myself, we've always been kind of leading spectrum at Virginia Tech. And this is an article that we wrote with Todd Humphreys, who's a professor at UT Austin in the Wireless Center, and he's an expert in aerospace and in satellites. And Shuai Ni, a former student of mine, who's at the University of Nebraska at Lincoln. And what it is, it's kind of an up-to-the-minute survey of what's happening in spectrum and 6G. So the motivation we all know for 6G, 6th generation, we're in the middle of 5G now. It's really starting to take off, especially the millimeter wave angle is really ramping very rapidly, growing at 40% a year. Very exciting growth in and around stadiums, urban cores. But 6G is going to have terabits per second. We're at multi-gigabits per second. 6G in 5 or 6 years, and now 6 years or so, we'll have terabit per second data. And the driving applications are augmented reality, virtual reality, digital twins, which I'll talk about, holographic telepresence, you know, like in the Star Wars movie, where you see Obi-Wan Kenobi appear in 3D. We'll have that in 5 or 6 years. A lot of sensing, a lot of integrated communication and sensing. And so with 6G, there will be a new spectrum band called the upper midband. First 4 generations of cellular had the FR1, frequency region 1, sub 6 gigahertz. 5G introduced millimeter wave. I'm fortunate to have played a leading role in the adoption of millimeter wave around the world. For 5G, that's called frequency range 2. The big hot new band is frequency range 3, upper midband between 7 and 24 gigahertz. It's where most all the investment is going on around the world. This will be spectrum unleashed. And when you look at the world above 100 gigahertz, that's another area that will probably start to become interesting in 6G. It may not be commercialized directly, but all the global standard bodies are going to start to be looking at the sub-terahertz region for the first time for mobile radio. And when you look at the frequencies above 100 gigahertz, you have spectrum wide swaths, 10 gigahertz of spectrum, much greater than we've ever had in the history of wireless. But you also have other uses, such as Earth Exploration Satellite Service, EESS, which is orbiting spacecraft looking down at Earth for weather prediction or sensing. These are basically wide open receivers that are very vulnerable to any signals from Earth that could mess up their passband. Or the Radio Astronomy Service, looking from the ground up to space, looking for the quasars and all the other things out there in deep space. So these are already using spectrum, and you can see the different blocks of spectrum that are basically off limits. Footnote in orange, you can see the footnoted frequencies in ITU, the International Telecommunications Union, where no mobile is ever allowed to operate. But wireless, with its huge data needs and its billions of people using it, want to get some of that spectrum up at the 100 gigahertz plus region. So there's kind of a conflict going on between how much spectrum will be available for the mobile industry, for fixed wireless backhaul, for fixed wireless access, which is growing remarkably around the world. 1 in 3 people will be connected by fixed wireless access by 2032. There'll be over 500 million people getting their internet over fixed wireless access. It's one of the fastest growing markets in the wireless industry. And these frequencies will be great for very wideband pipes. So there's this tension between active and passive receivers used by satellites, terrestrial, and then the mobile networks in space. This has been one of the exciting new developments, and Virginia Tech has a great history in mobile satellites. In fact, when I was hired in 1988, two professors, well, three, Charles Bastian, Warren Stutzman, and Tim Pratt, had one of the best satellite communication research groups in the country in Blacksburg. And they were looking at mobile satellite. And now, 40 years later, their vision is actually coming true in 6G, where our phones will have direct-to-device, D2D. Chips are already being made, shipped in Apple phones, Android phones that talk directly to a satellite. So this idea of global satellite communications, supplemental coverage from space is one of those new FR3 upper mid-band spectrum opportunities. Now, at NYU, we were one of the leaders in developing knowledge for this new frequency band that will be a part of 6G, the upper mid-band, or FR3, frequency region 3. I had a sense of where the spectrum bands would be before ITU ratified them at the WARC conference, WRC's World Radio Conference. And so we were out measuring the streets of New York, providing multipath data used in joint communications and sensing work. And we've got this massive database, nearly a half a terabyte of data in both 6.75 and 16 gigahertz. What the multipath looks like, what the angle of arrival, what the angle of departure looks like. And sure enough, in the last year, these different government regulatory agencies have identified this FR3 spectrum band as the key places where new auctions will happen for, it's probably not following me, is it? There we go. So now it'll follow me. Sorry out there. Anyway, so we have this huge data trove that a lot of our industrial affiliates at NYU Wireless are using to develop antenna systems, diversity systems, joint communication and sensing, and so on. It's a sliding correlator system that I actually developed for the first time at Virginia Tech in the 1990s, and I'm on the 5th generation of channel sounding gear that students have built over the years. So just like we're on 5G, I'm on the 5th generation channel sounder. We're going to start working on the 6th generation. It's a spread spectrum system, which allows me to get experimental licenses very easily because it's very low probability of intercept, very low power spectral density. Now, this direct to device from satellites is really heating up. If you look at Elon Musk's Starlink, I think they're up to 8,500 satellites launched. And on a beautiful clear night from my house in Reiner, Virginia, I can look up and see dozens of satellites flying by, these low Earth orbit satellites. And then another company called AST Space Mobile is building phased arrays that are literally almost the size of a football field. This is a picture of not their latest, but the current satellite antenna, 64 square meters. Those are people in the back. These are being launched, and AST is working with T-Mobile now to provide direct-to-device satellite. And there's two schools of thought. AST is looking at building these very, very big phased arrays, fewer satellites, low Earth orbit, for direct connectivity with very, very narrow beams, trying to make the cell site from space relatively small, only about 50 kilometers, which is, you know, you think from space, that's very low coverage. And the key thing about cellular, the reason why wireless has grown to where it is the idea of frequency reuse. You know, back in the early days of cellular, you put the tower on the tallest building. In New York, you put it on the Empire State Building. And you had a very, very large coverage region. But as you shrink the cells and lower the towers and make microcells and picocells, you get to reuse that same limited spectrum a few kilometers away. That's the whole idea of cellular. So if you can do that from space and start getting spot beams, you reduce the size and you can start reuse the spectrum to get much more capacity. And that's AST's vision. Starlink uses very directional phased arrays and lots of satellites. So they're able to do multi-user or combination, combining distributed MIMO from space to get capacity. So they may not have as great directivity as these large beams, but they're able to use lots of satellites listening to the same or transmitting to the same equipment in order to build coverage and capacity. Two different approaches, both effective, and both have gotten a lot of interest. But there are challenges, bandwidth scarcity. So you see during this, this latest spectrum deal with the EchoStar and the spectrum being sold, you're going to see Starlink trying to buy spectrum. They're going to start to try to build a giant cellular network out of space. And they're trying to get spectrum in this upper mid-band. You're going to see a lot more of that around the world. Interference with terrestrial cellular. You know, will the satellite interfere with the ground-based? Do you use different frequencies? This is all up for debate, and there's different theories. Very exciting research area, especially given that the device we carry in our hand has only so much antenna gain and only so much power that we can use. But this is coming and will be a big part of 6G. We talk about that in the paper, all of this. So if you look at the FCC, it started last year looking at satellite operators integrating with the terrestrial networks, led by proposals from Starlink and from AST. In fact, if you watched the Super Bowl, did you see that amazing ad? T-Mobile said, try our new direct-to-satellite. All you Verizon customers, come for free and try it for 3 months. That was on the Super Bowl ad, T-Mobile advertising it, and that was using the AST giant antennas to give free text messages. They're trying to get customers, and it's worked. But this will be fascinating. You'd get seamless coverage. You know, when you're on a cruise ship right now in the middle of nowhere, you have to pay $10 a day for the boat's internet. Now you'll be able to use your cell phone and talk directly to a satellite with your normal link. Or if you're on the lake or a river or in the desert, you'll have coverage. But there's a lot of Doppler and latency. So these are great research areas, and there's a lot of work going on that right now. In Europe, when you look at the terahertz spectrum, FCC got out in front. 2019, I was fortunate to be a part of it, helped lead the FCC to open up the bands above 95 gigahertz for the first time in the US. So we have experimental licenses throughout the 100 to 240 gigahertz band. So right now in the US, you can get a product. You can't do that yet in Europe, but there are products being made for Wi-Fi of the future and sensing, and you can do that in the US with an experimental license. Europe is not there yet, but they're almost. And this is something they're looking at the agenda at the World Radio Conference 2027, looking at the bands from 100 to 900 gigahertz and trying to determine where in these regions can they open it up for fixed and mobile wireless communications. You can't have wireless without spectrum. So the fact that the governments around the world are looking to open up this band virtually guarantees that in your lifetimes, we're going to be going way up above 100 gigahertz. And when you get to that frequency range, the antenna sizes become the size of a human freckle. And you can put a lot of freckles on a cell phone and make very directive beams. And you can carry a lot of information with low battery power at these frequencies. So these massive data rates needed to do virtual reality, digital twinning, huge downloads, AI are all going to be supported at these frequencies above 100 gigahertz. And NASA is really protecting the Earth experimental and the censoring and the radio astronomy. Other governments are protecting it. So there's going to be kind of a wrestling match to figure out where in the spectrum you can be. And I've kind of looked ahead and believe that these are where we're going to be operating. These will be the bands in the next 10 years, I believe. And I'm investing in equipment here. We'll be doing some field measurements in these areas over the next few years. I believe there'll be 3 new bands, 180 gigahertz. If you look at 180 gigahertz, there's a problem and a wonderful benefit. The problem is at 180 gigahertz, you share it. If you look at that gray line, that's what that white line, that's actually a reserved band for sensors from space, these very sensitive receivers. But if you also look at that frequency of 180 gigahertz, there's huge attenuation. There's about 100 dB per kilometer, which means anything on Earth is not going to interfere. Figure there's 3 or 4 kilometers of a troposphere to get through to a satellite, even on the slant path, or even directly ahead, and you're down by 400 dB. So it's impossible for a space-based receiver to see anything on the ground because of the natural attenuation of the troposphere. The troposphere is this amazing protection that God gave us from 0 to 6 miles above the Earth, where galactic rays don't harm us, and we're not impinged by the radioactive energy that's in space. We have this natural protection by the troposphere up to about 10 kilometers. So going right up, even if you go through the troposphere, there's no way a signal could be seen in one of these space sensors. Now, getting NASA to believe that's a challenge, but it's the physics of the thing. So you could have what I call whisper radio. Radio waves just traveling within a few meters or tens of meters that attenuate very rapidly. They carry huge amounts of data in this 180 gigahertz band, which is not hard to engineer. And so you can imagine replacing wires in data centers, replacing wiring in tanks, in cars, in trucks, to these lighter wireless devices that are carrying huge amounts of information locally and not interfering because of the natural attenuation. Then we have 220 and 280 gigahertz. If you look on the screen, these are the largest swaths of contiguous spectrum that exist today that are allowed by FCC and ITU rules. So these are, I think, the future bands which will support backhaul, front haul, wireless, Bluetooth, Wi-Fi of the future with huge data rates. Now there's a lot of challenges, which is good for all of you in the room doing research. There's hardware, technology barriers. You go up to terahertz, it's harder to make efficient amplifiers. It's just a function of the semiconductor material. We're getting better. DARPA has funded a lot of research over the last decade that gets power amplifiers up to several hundred gigahertz. It's still expensive. Noise, phase, mixers, oscillators are noisy. There's a lot of phase noise. It's hard to make cheap consumer-grade electronics. But that's what they said about millimeter wave. They said that about 5G. We can't put 28 gigahertz in a cell phone. If you have a high-end Android or Apple, you have a millimeter wave transceiver and 16, maybe 32 elements of antenna, and you're doing multi-gigabits per second, and they said it couldn't be done. So we can do it if there's a market. A to D, D to A, bandwidth. Things get more expensive power-wise as you get more bandwidth. It's a natural law of physics. But when there's a will, there's a way. And we get the benefit of beamforming with these very directional multi-element antennas. And then the device to direct-to-device issues, we've got to figure out where they're going to fit in the spectrum because we have these existing protected bands throughout the spectrum. So a lot of opportunities for research, a lot's going on, and that was kind of a survey of what's happening in the world of spectrum. That's what that first Nature Partner Journal talks about, everything that's happening around the world. So if you want to know what's happening in spectrum, check out that paper in Nature. We kind of give all the references, kind of laid it out there on what's happening around the world. And some of the research directions that fall out of this are clearly we need to look at the new channels that'll be used for upper midband FR3. No one's done work in the suburban market. There'll be a lot of suburban use, a lot of fixed wireless access use. No one knows what's happening in rural. Waveform design. ISAC is very exciting. Integrated, the idea of using sensing and communication integrated on the same signal. I'll talk a little bit about that later. But this is a huge area where your phone using a communication signal also is acting as a radar, figuring out what's around the corner, what's happening in the environment. That's all coming to a cell phone near you in 6G. And then one thing on the bottom, energy efficiency. With AI, the cost of compute has gone through the roof, and I've given talks about this. We've developed a new figure of merit called waste factor. It's kind of like noise factor. It's a new theoretical, very easy to use construct, which allows for a unified metric to determine the cost of power or energy in any communication network. We all do research, but we never really figure about how much power we're burning from the power grid. Right now, AI is blowing up, and no one's really got a metric on how much it costs to compute and how to minimize that. Our field, the ICT industry, is going to be 10 to 20% of the world's power grid consumption in 5 to 10 years. Right now, we're 5%. The whole world's going to be looking at us and how much we power. But none of us as researchers look at characterizing the amount of information, amount of energy it costs to send information. So we've developed a theory on that that's just starting. So, okay, so that's the first paper. Let me conclude and just say the upper midband's very exciting. It's the sweet spot for 6G. You'll hear and see a lot about it. Terahertz is the long-term enabler with ISAC and the future of short hop and also mid-range communications, eventually mobile in 15 years from now. And so these are some exciting directions. Now for something completely different. Yes, question.
Just one question about how is the policy interacting with the technical advances?
Yeah, good question. So just on that first paper, I talk about that in the paper. How is spectrum policy and governmental policy working with the technical advance, the technology advances? Policy generally lags technology development, but the FCC has been very good at getting out in front of the technology with rules that allow the advancement. For example, the FCC doing millimeter wave opened up millimeter wave before the rest of the world, which led to the technology development. Just like going up above 95 gigahertz in 2019, that opened up the licenses which are now creating investment. That's rare. Most of the world stage tends to lag and waits for the technology developments to pull them in. And we talk about that in the article. Thank you. Okay, second paper, something completely different. Site-specific location and validation of ray tracing using a new tool we've created called NYU Ray at the upper mid-band frequencies. This is work by my graduate student team. And back in my very early days at Virginia Tech, I was very fortunate to really pioneer the idea of ray tracing. Ray tracing is where you take a three-dimensional model of the world, and then you render that model of the world in a computer, and you synthesize radio wave propagation in that model of the world to predict where energy will arrive and how strong. And even though Motorola claims to have published the world's first paper on it, Lee Hamilton, it was actually my idea, and they came to Virginia Tech and took it and then wrote the paper. And it just happens. I was very grateful Motorola gave me funding, but they didn't include that. But I taught them ray tracing. And then my first students went on to do ray tracing. I started a company called Wireless Valley that was a ray tracer, and Motorola bought it. So Motorola did pay me at the end. Well, thank you, Motorola. But ray tracing is now really the state of the art in designing and predicting radio networks. And I wrote a paper in 2006 that predicted that ray tracing would eventually run real time in a handset so that you could have a model of the world and predict on your phone virtually in real time what the coverage is going to be and how to deal with handoffs and interference. That will happen. I see it now with AI so much. But this is a key work that has attracted a lot of attention in the industry. So by having this great measurement database of the real world in New York City, in our office lab, in a factory, the makerspace, the campus, outdoor environment, we have this high quality gold standard data. We have world-class quality data that's very expensive and hard to get. And once you have real world measurements, you can train AI, you can build accurate models, you can make predictions that go back and predict that data. You really have to start with gold standard measurements to do anything great in predicting radio wave propagation. Because radio wave propagation is so random, you give me a case, I'll give you a counter case. I mean, radio waves, it almost seems random, but there's a lot of structure because it's physics. And so you try to recreate the physics in a ray tracer. So we use the measurements, we understand ray tracing because I've been doing it all my career. And then we found that if you calibrate the location of the synthesized or simulated base stations and mobiles based on measurements, you can actually validate and remove some of the vagaries of the 3D environment and the measurements. You kind of remove all the randomness and drive it to a more accurate model of the real world. And this is important for digital twinning. If you think about digital twinning wireless, you're going to need a model of the environment, a model of what happens. And so you could kind of start doing network simulation, network deployment, network vision with a computer and let AI figure things out. So we're trying to make the ray tracer work better. And so we've come up with this new approach using the measurements and then driving that for optimizing. Let me see if this video will run. I don't know if we have audio on this or not. We'll see. Can you see the video? This is how hard it is to make measurements. As a team, let's see if it goes, maybe it's a memory issue. It's pretty cool because well, let me just skip that. You can go to the QR code if you want. This is on the web somewhere, but it's very, very painstaking. Each one of these locations on the map take 4 hours. We very meticulously point the directional antennas in every azimuth direction at the transmitter and receiver. We go in vertical half beam width above and below at both transmitter and receiver. This is the NYU Brooklyn campus. And we very meticulously capture the spatial and temporal channel impulse response, H of T, which is the key to anything in wireless. Any communication system, sensing system needs an impulse response. 3GPP makes a statistical channel model. Well, it turns out that's a model by committee, not based on measurements. Well, part of our work is trying to get the global industry bodies to put all their data in a standard format so it can be machine learned. We're hoping that takes on traction, but right now, people do their own measurements, they don't share the data, and so you get a model by committee, which everyone uses, but it's not accurate real world, not at all. So we've made all these measurements, and this is the channel sounder 5th generation. It's a sliding correlator, and it doesn't look like much. It looks like the Ghostbusters. If you've ever seen the movie Ghostbusters where they're trying to get the ghosts, that's what it looks like. We wheel this across the streets of New York City. You wouldn't believe how many times we've been stopped by people afraid that we're doing something bad, or the police or fire will be like, what are you doing? It's like, we're authorized. But, and so we created this ray tracer. We call it NYU Ray. It's now on the 2nd generation of students. And you're able to put into a computer model the 3D world, and then you're able to launch rays and see what happens to the received signal. We're writing it in Python. We have various engines, and you can see you're able to put in the scene, model all kinds of propagation prediction. And it's exciting because I've done this all my career, and now finally we're at a point in time where computing is not the limiting factor. When Jeff Reed and I were starting the Wireless Center in 1992, I had a lab with 12 Spark workstations all running parallel processing to do ray tracing. Now you can do it in a matter of minutes. And what we do is we use the OpenStreetMap by Google, which by definition has some errors on its accuracy. It's a mesh file. We take photos of common objects, which are hard to get into a computer model. We put it in Blender, and together the maps and the objects create a Blender model. And so we have this outdoor 3D map, and we then turn this model into an XML file, which is very easy to run, very compact. And we use the initial transmitter receiver coordinates based on our GPS. We map it to where it is in the synthesized Blender world. We know there's going to be errors. We simulate the omnidirectional propagation in the ray tracer. And then we use our measurements, our actual field measurements, gold standard measurements, to determine how to optimize that computer model, to figure out where were the transmitters and receivers compared to what the noisy 3D environment is, because it's always going to be noisy and incomplete. What's amazing is my grad student Mingjun Ying came up with this loss factor. It's a total heuristic. We're trying to find the optimal loss factor, but this loss factor looks at the shape, the peak powers, the duration of the multipath delay. It looks at the different characteristics of the impulse response, and he came up with this heuristic, trying lots of things, and he uses this loss function to then tweak the transmitter and receiver locations in the 3D environmental model to match the measurements. It's a clever idea. I don't think it's ever been done before. We got the idea from medicine. When people look at the efficacy of drugs, they look at a trial with hundreds of patients, and then what they try to do is they try to figure out what's the drug and what's the outside noise or other conditions of the patients. And what we found is, if you look at this graphic on the far upper right, the red is what the prediction was before you apply this, if you will, optimization of location based on measurements to tweak the transmitter receiver location. So that's where the simulation was in red before. And then when we did the optimization, minimizing the loss function, you can see that the energy predicted lines up exactly at the peak of where the energy was received. Now, this is just on the strongest multipath component, but you can do it on all the multipath components and the total power. And so this is a very effective way to, if you will, tune the synthetic model or the digital twin of the real world if you have measurements. And you can see we lower that we get 1 dB better in the prediction. In line of sight, we go from a 2.4 dB line of sight error between predicted and measured down to 1.4 dB. We shave a dB, that's 25% of the power. We actually drive the prediction to be better with simply having a few sparse measurements, only like 18 points over the map. So that's a very exciting. It shows that you can use data to tune the geometric model, and you could eventually learn on this. And so this is the interface we have on NYU Ray. You can put in the databases and the receivers and transmitters, and we can run it now. And so the students are working. I've got a team of undergrads working with a couple of grad students to work on improving this NYU Ray. And it's all in Python, so we can do ML on it. And here's the proof of the pudding. These scatter plots show you the path loss validation. It's hard to see, but you can see, if you look carefully, the green scatter plot on the left, the green line is measured line of sight. This is the measured line of sight path loss around the streets of New York City at 18 different locations. And you can see what the ray tracing does to predict the line of sight at those same locations. The ray tracer predicts very, very closely the line of sight. No surprise, line of sight's easy. But look how off the 3GPP model is. 3GPP in line of sight will predict much greater loss. If you look at 1 kilometer, it's about 10 dB more lossy. And if I didn't train the ray tracer, it'd be somewhere between 3GPP and the measured. But it gets closer to the measured as I train it. Look at non-line of sight. Non-line of sight is the real litmus test. Look how well the ray tracer does in non-line of sight compared to measure. If you look at the measured non-line of sight, it's that red dash curve, and the ray tracing non-line of sight is very close, even at 1,000 meters. 3GPP is much lossier. So it shows that ray tracer can actually start to recreate measurements very accurately. NVIDIA doesn't do this with Sonera. No one is doing this. They don't calibrate. This is calibrating the ray tracer with measurements, and it's calibrating at the same time the physical model, which is where a lot of noise is. And then we borrowed this from the medical community, get rid of a few of the outliers. If you do outlier removal for angle spread and delay spread or RMS delay spread or whatever the channel parameters are, what you can see is you use these different ways to get rid of a few of the errant points where the ray tracer really misses. The ray tracer maybe didn't have some artifact in the environment that's really in the environment. Maybe it got behind a tree and we didn't have the tree modeled in the ray tracer. So if you throw out a few of the outliers, and there's different approaches to get rid of the outliers, and we talk all about this in the Nature Partner Journal, which you can find online. And you remove a few of the outliers, look what happens. you get a remarkable fit to the statistics. These are what 3GPP tries to do, but you get a remarkable fit. You start pushing the median closer to where the measured were. The Kolmogorov-Smirnov coefficient starts going closer to 0. You get your p-value, the probability that's from the same distribution goes up. Basically, you're able to improve the distribution modeled by the ray tracer to what was actually measured. So you're able to make a ray tracer more accurate, which is going to be vital for circuit design. Think about it. If you're building a circuit, Jeff, you're building a circuit and you want to know what the real channel is for your amplifier to work, or you could start using AI and start using these channel models and bring them right in to your system design and see how the circuits do in real world. Or if you're building a receiver and you want to see how diversity is going to work, or massive MIMO, or multi-user MIMO, multi-user detection, you can now have a better estimate of what the channel will be using a ray tracer. And the beauty of a ray tracer is you can learn more from data, measured data. You can keep driving and improving it. And that's what my company did at Wireless Valley about 20 years ago. And similarly, angle spread is also very good. So we've now got a method which allows us to take a physics-based ray tracer and start to integrate it with data. And we're trying to create a standardized format where other people who are making measurements or doing simulations with the impulse response can represent that data so people can start sharing it. And these measurements at FR3 allowed us to build the ray tracer, which has less than a 0.14 difference in the path loss exponent. Instead of 2.0, worst case it's 2.14. These are very good predictions of power over distance. So it's a very, very strong approach. It hasn't been done before. We think this offers a way forward to make synthesizing digital twin simulators much more accurate with just a little bit of really good data. Anyway, so that was number 2. And here's the third and final paper, something completely different. This also is in Nature. We're looking at the proofs now, but it's on ArchiveX. This is using this idea of waste factor and waste figure. These are new metrics. I really hope you'll look at it. My belief is these will be in all the textbooks in 10 years. This will be as fundamental as noise figure, I believe. Because our world needs it and we don't have it. It's a fundamental metric that you and I can all talk about how much energy we're wasting when we have information from a source to a sink. How much information is being sent and how much power is wasted? So let me ask you this right now. If I have a transmitter and I have a receiver and I get the exact same power at the receiver as I sent from the transmitter, how much did I waste? If the total power gets to the other end, was there any wasted power? 0. Thank you. There's no wasted power. That's the utopia. In fact, if we could transmit information from any source to any sink, and all of the energy goes into transmitting that information, and 0 energy is wasted on any other component or path, that's perfect sustainability. No waste, right? That would be a waste factor of 1, unity. Anything bigger than 1 represents more wasted power than the ideal. So that's the idea. Just like Harold Freese had the idea of noise figure in 1944. Harold Freese came up with the idea that if you have a noisy input to a receiver and you have an antenna and you have a receiver, noise figure tells you the additive noise from the input to the output, right? And a noise figure of 1 means there's no additive noise, right? A noise figure of 1 means perfect noiseless. Well, in 1944, the enemy of wireless was noise. We didn't have wideband. We were doing shortwave. We had tubes, no transistors. So noise figure was this great metric. It took about 10 years to take off. But people realized if you lower the noise at the detector, you get better signal-to-noise ratio. So you want to make F, the noise figure, as low as possible. Well, now, 100 years later almost, we don't have the enemy of noise as much as we do bandwidth and power, right? Everything's interference limited nowadays. In the early days, it was noise limited. Now our big enemy is going to be fossil fuels and pollution and the global consumption of energy. So here's a figure of merit that's based on exactly the same mathematics as noise figure, but it now, instead of measuring noise addition, it computes wasted power addition. And here's how it works. It's a very simple definition. It's waste figure or waste factor in linear value. 10 log of it is waste figure, just like noise figure is 10 log noise factor. Waste factor is simply the power to deliver the signal over the path, the total power consumed to deliver the power of the path divided by the power in the signal. It's the total power used on a source to sink versus the power in the signal at source to sink. If the power in the path is equal to the power in the sink, in the received signal, it's 1. Any additional power that's wasted or burned goes into P path, and W is greater than 1. So if you look at a cascade with a source and a sink, and the sink is the PS or power out, that somehow it flipped. You have this wonderful cascaded formula, which looks just like noise figure on the right, but it's now waste figure. So you compute the added power that's wasted from the source to the sink. And it's got this beautiful recursive formula, which is identical to Free's noise figure, except we're looking at the output power, the power out of into the sink, the power of the signal. So we refer it to the output. Harold Free's always referred it to the input. But guess what? Input and output are just related by the gain of the cascade. So just like Harold Free's, you could relate to input or output. This is a very powerful, simple metric. And believe it or not, W is simply 1 over efficiency in most networks, which means if we know the efficiency of a component and the gain of a component, any circuit, any system, you can build the total power consumed and power wasted from a source to a sink. We've looked at it for oscillators, communication systems, data centers. This is very, very promising. It's fundamental. I encourage all of you to look at the power consumption in all the work you're doing. When you're doing multiple users, massive MIMO, look at the power being consumed. Try waste factor to show and start using it as a metric, because it's going to matter someday. In fact, just like in noise figure with Harold Free's, where it's the first component at the noise source with high gain that governs the whole noise figure, in waste figure, it's the component closest to the sink, the high power amplifier that's closest to the sink that's high gain. That dominates waste figure. The math is elegant, it's very easy to use, and no one's ever had a unified metric for understanding wasted power. That is the power on the source to sink link that's wasted. We need to start thinking about it. Now, the beauty of waste factor is it now gives us an analytical tool which lets us look at any circuit, any amplifier, any communication system, and unlike Harold Free's, who limited noise figure to the receiver, waste figure works transmitter, channel, receiver, because the channel is part of the cascade between a source to a sink. So for the first time, we now have a metric that will include the channel. So you can look at multi-user distribution, multi-user architecture, and figure out the total consumed power. And it shows that small cells are much more power efficient. Lingqi.
In fact, actually, beamforming is trying to reduce waste figure, right?
Right. Beamforming wants to reduce waste figure, and that comes out of the fundamental theory. A more narrow beam gives you more gain in the channel, which reduces the waste figure, reduces the power consumption, and that's in our 2024 paper. And it's all, so we use this with colleagues at Texas A&M. That's exactly right. You reduce waste figure with higher gain because you reduce the loss in the channel. Now, we came up with this idea about 10 years ago, 15 years ago. Brilliant student named James Murdoch when I was at University of Texas. We came up with the consumption factor, which relates the data rate through a channel of the power consumed over the channel. In other words, it maps power consumption to Shannon's limit. Shannon's limit deals with capacity and signal to noise ratio to how much information you can get through a channel. Using the consumption factor, you now have a metric which allows you to, if you know the power consumed along the channel, you can relate it to the maximum data rate you could get. Well, waste factor ties consumption factor into Shannon's limit. And now this is something you can measure, you can model, just like noise figure you can measure on an analyzer. You can measure waste factor. You can measure it by looking at the output power and the power consumed. And it allows AI to learn. You could do real-time monitoring of power. So we decided to use this idea and start to look at some practical commercial links. And by using the consumption factor and waste factor, we came up with this expression of the minimum consumed power along a source to link. And it's related to the signal to noise ratio and the waste factor and the power of the noise. In fact, you can see it comes from Shannon's limit. We all know there's an additive white Gaussian noise. R max is B log 2, 1 plus SNR. You can rewrite the consumption factor using Shannon and figure out the data rate and the consumed power. And when you take it to the limit of the wideband case, which is what Shannon did to find the minimum EB over N0. And by the way, channels are all becoming wider bandwidth, right? The world's going wider bandwidth. So if you take B to infinity, you find out that the reciprocal of consumption factor is this expression. The power that's not in the path, that is all the power not in the path but being consumed, divided by the capacity plus ln 2 n naught W. This is an exciting fundamental new expression that can be used to determine the bounds or the limits on energy consumption in any source to sink link. This is fundamental. And when you do that, when you use this fundamental definition of the Shannon limit without additive waste, it's this famous expression, ln 2, right? Ln 2, that's EB over N0. But when you consider the additional wasted power on the source to sink, you get this result. It's the same as Shannon's limit when W goes to 0, when W goes to 1. When W goes to 1 and you have no non-path power, that is all the powers in the path, all the powers in the signal, there's no waste. That goes to 0, that goes to 1, and you have the actual power consumed. EBC is the actual power consumed. It goes to the Shannon limit of EB. So here's an expression now that includes the actual wasted power from the source to the sink to give us a new bound on the energy consumed for the maximum possible output. So we put this to the test, and we noticed that in a wireless link, you can include the channel because the waste factor of a channel is 1 over the gain of the channel, which is equal to the loss. So the waste factor of any channel is just the propagation loss in a channel. And when you do that, you come up with this amazing expression for the practical energy per bit consumed limit. And it's based on the waste factor of the transmitter, the gains of the channel and the receiver, and the amount of power wasted, the non-path, the power that gets wasted in transmission. So this is pretty cool. It shows fundamentally what you said, Lingqi, with that high gain receivers are critical, and millimeter wave beamforming gains can more than offset the free space path loss and vastly lower the waste factor. So these very directional antennas, which will happen at terahertz, are happening at millimeter wave, will happen in the next 10 or 20 years, are just by their nature with the directionality, much more energy efficient. And this is a theory that shows you how much. So we decided to look at the problem that I keyed up about 12 years ago with James Murdoch. How do you know when to use a relay? When is it more efficient to put a relay in between a source and a sink than to just allow the source and the sink directly to communicate? That is, where's the decision to save energy if you're going to build out a network? Do you connect directly or do you put a relay? And you consider the power consumed of all those devices. So we decided to use it with this new result. And it turns out there's a formula. It forms an ellipse. That is the distance between the D3 is the direct source to sink. If the distance is greater than this ellipse made by the two D1s and D2s for a given path loss exponent, you can find the optimal location where to put a relay and have less power consumed than if you made the link directly with the same signal noise ratio. This is very important for reflective intelligent surfaces. It's important for routing. We now have a theory to actually understand the power consumption. And when you do this, it turns out that if you use actual practical values, the source, that X on the left in the purple, and the sink, the receiver in the dot, these colored regions tell you for the different waste factors, depending on how good the equipment is of the relay, how energy efficient it is, where you would put the relay. So in these colored zones is where you would put the relay to save power. You learn a lot from this. For example, you see that if you have a very, very wasteful relay, a very cheap commodity device, and by the way, we showed last year that most base station infrastructure equipment made has a waste factor of about 3 or 4. Base stations have a waste factor of 3 to 4. Our cell phones have a waste factor of about 15 to 20. So all the cell phone industry is putting more waste on you, the consumer, than they are on the carrier that's paying the electric bill to run the cellular infrastructure. So these are cheaper, easier to make than the base stations. So they're noisier, they're more wasteful. And so look at that orange or the gray circle right there at the dot. That's the zone where you put a very poorly designed, very wasteful, look, W of 100, the W relay of 100 in the scale. That's where you put a relay closest to the sink and still save power. Even with a very wasteful relay with a W of 100, you put it over here in this little zone by the receiver. And guess what? That still saves you power. And this is what fixed wireless access is. Think about it. Fixed wireless access takes a signal, maybe a couple kilometers from a base station, and then you have a little cheap box in your window, and then it radiates over Wi-Fi in your home, right? You buy this cheap commodity box to get the local coverage close to your receiver. So this is like a fixed wireless access downlink. This gave us a lot of insight to study that because that's a relay channel, if you think about it. By the way, here's some results, not looking at the waste factor, but looking at the gain of the relay. Look at the gain of the relay. This is now looking at G sub Rx, and there's a receiver on the right. What you can see is with you have very low gain receivers, like gain of relay only 10, it has to go closer. It has to be closer to the sink. It has to be closer to the receiver. I mean, this kind of tells you intuitively what you'd expect, but now we have a mathematical construct to actually optimize and study any kind of network architecture. You can see if you've got high gain relays, they can be far away and even behind the source, a longer propagation distance from the source to the sink, and it's still more power efficient. So fascinating to see the theory being used. So let's look at fixed wireless access. It's growing rapidly. I told you it's going to be 30% of the world's internet connection in the next 7 years. That may be low. I think it'll be more. Fixed wireless is already one of the biggest drivers of revenue for 5G. Verizon, AT&T, even T-Mobile buying US Cellular is all looking at fixed wireless. I want to get fixed wireless. It hasn't come to my home yet. I need it in Reiner because we don't have very good internet at all there. I want fixed wireless to come, and they're just trying to build the infrastructure. 5G is the spectrum. It's there. Millimeter wave is very popular. So fixed wireless is coming, and let's take a look at fixed wireless using the waste factor theory. So let's look at uplink and downlink. I saw some great work in Lingjie's lab. You students are doing really exciting work here. Makes me very proud to see where our wireless center came since 1990. 35 years ago, to see it sprouting like this. It's amazing. And so you'll like this. I'm looking at uplink and downlink. And let's say we look at the percentage of traffic uplink, percentage of traffic downlink, where row up and row down equals 1. And so you can use that same analytical formula to figure out the optimal location for a relay for different bounds of traffic. And we're going to swap the roles of source to sink, whether it's uplink or downlink. And we use this theory, and now you can see where it makes sense to put the relay. So here you can see on the left, this is uplink of 0, downlink of 1. So on the far left, this is the case of where you'd put a relay all downlink. This is downlink from the base station. And that's the optimal place to put a relay or a fixed wireless access node to get into your local home using realistic values of the waist figure for transmitters and receivers. These are realistic values. And for uplink only, uplink, you'd want to put the relay closer to the source, to the, for the uplink only, you want to put it at the receiver, around the receiver. So that's the optimal place. And so the carrier can put the burden on you to pay for the power for the downlink only reception. And that's what happens. So I just wanted to tell you the takeaways on this is waste factor is a unified energy efficient metric. And we've shown through a number of cases in the literature that you can use the waste factor in so many different applications. I don't know why that ball's bouncing, but I kind of like it. It's helping me make the presentation. So it's a very convenient cascaded formula. It works for all kinds of environments, including fixed wireless access, and it's really going to help on 6G energy aware networks. And with that, I'll wrap it up and say thank you, and I hope this was informative. Take a look at these papers. They've all appeared or will appear soon in the Nature partner journal called Wireless Technology. They're online now, and I hope you find it useful. Thank you. Yeah, I'm pretty much on time.
Yeah. Does anybody have any questions?
Yes, Professor Reed.
Have you looked at the waste factor for IAB?
Have I looked at the waste factor for IAB, integrated access and backhaul? I've not looked at it. We have looked at it for UAVs. Nokia looked at it a few years ago. By the way, there's a big error in that paper. They made a mistake in a reciprocal, and we fixed that error in the Nature article. And we used it for unmanned aerial vehicles and found it's better to use a repeater than a whole new base station. It's more power efficient. And power efficiency is very important on a mobile platform in the air. So we did use it for that. Turns out the math was wrong, but the conclusion was right. We fixed that in the Nature paper. But I've not looked at it for integrated access and backhaul. Jeff.
I want to ask a hardware question. I'm really interested in the terahertz work that you've done. The practicality, though, so scaling up to large numbers of antennas is great. But what are the phase noise or delay requirements that you have on a per element basis in order to realize the beamforming gain or aperture?
Yeah, so the question relates to the phase noise tolerances and kind of the state of the art in getting to build multi-element phased arrays antennas. I have not built those antennas. I'm actually building out a measurement system first to be able to do that. So I don't know the answer to that. I know it's a challenge. I wrote an article in 2019 called Opportunities and Challenges Above 100 gigahertz. You know that paper? Yeah, I touched on it, but I didn't go much into depth because the technology is changing so much, but it's going to be a challenge. And that will, the phase noise and actually the losses are likely to be the limiting factors of the practical beamforming gains that you can get. And I suspect we're going to have to do a lot of free space beamforming outside of the container of the actual antenna elements to realize the best performances of those. There's challenges associated with that. So I don't know the answer to that yet. I don't think a lot of people do. Maybe you know. Do you know?
No, it's a very tough.
But it's a very tough problem. And then you get into the issues of frequency selectivity across wide bandwidth and trying to maintain gain and phase over bandwidths that we've never used before, you're going to have frequency selective issues over a 20 gigahertz passband. That's another challenging issue. So lots of exciting things to look at, but I have to believe that first you need to be able to measure it really well, and I'm working on that with our MRI terahertz grant at NYU.
Okay, I have a question on Zoom. Have you ever achieved a waste factor of 1? What kind of special measures did you take to do it, if so?
The only way that I know of, and I've never done it personally, but the only way I know of to obtain a waste factor of 1 would be able to go down to about 0 degrees Kelvin and transmit across a perfect conductor. I think that's going to be the only way we get there. So in practice, everything's going to have a waste factor greater than 1. We can really reduce the waste factor in a lossy channel by getting gains of the antennas. Fiber optic cables are likely to come close to 1 if they're designed right and operated in the right regime. But waste factor is very new. The world hasn't really caught on to it. I'm counting on the research community to acknowledge that we all have to own the carbon footprint of our industry and come up with a common metric of energy consumption, not just in communications, but in computing. Right now, the entire over-the-top industry, the data centers, the large servers, the people that distribute web content, they use a metric called PUE to evaluate the power efficiency of data centers. As we wrote about in 2024, this common metric that all the giant companies that are consuming huge powers for AI use for their data centers is PUE. PUE is power utilized efficiency or something like that. I forget what it is. I write it in the paper. We show how PUE masks or basically obfuscates the chore in the data center, which deals with cooling, no information, cooling, the power consumed in memory, no information transmitted in memory, and the power consumed by the IT communication path. And in the end, the data center's job is to communicate energy. It's a source or a sink, right? But right now, the metric used around the world, PUE, masks that. It's all glommed into one number. If you start parsing it and look at the amount of energy used to transmit the bits versus how much is in cooling and how much is in storage, you find out that the metric is flawed. You find out that a data center that consumes more power is actually more energy efficient because it's moving more bits and it's got better IT power efficiency. Right now, the industry misses that. So while we build all these giant power plants for the AI future, the basic metric being used to figure out if a data center is accurate is missing the fine granular details that waste factor reveals. Waste factor reveals the power on the source to sink path and then uses superposition to find the power consumed by the components off the source to sink path. You add them all together, you get the power consumed. Right now, the data center industry is missing that. Right now, the AI compute industry does not have a common metric of energy consumption for when you use ChatGPT or when you use an AI query. There's no common metric. We have a volt, we have an amp, we have an ohm. Those are common metrics used anywhere. We do not have a common metric for what compute costs. And if you ask someone, they'll say, well, it's a energy nanojoule per token. The trouble is each token is not equivalent in AI. Some tokens have much more value than other tokens. We're missing a fundamental metric. So I would encourage all of you to look into waste factor, consider using it. We've written a few papers on it, but it's slow to catch on, just like Harold Freese's work was slow to catch on. He had the advantage of being Bell Labs, which was the only industrial researcher in town in 1944. Now, everyone does research, but companies don't publish their research so much. So I encourage you to look at that. But thanks for the question, Jeff. Yes, sir.
Hello.
Hello.
Thank you for the talk. In your previous slides that you showed the position of the relay and the UE and the base station.
Yes.
So are you assuming that the relay and the base station are operating in different frequency bands or the same ones?
Yeah, well, I'm making the assumption they're in the same band for this analysis. Actually, there'd be a translation, so the path loss might change a little bit and the power might change a little bit. But for the analysis, we're assuming it's just in the straight same band.
So are they being separated in time then, in terms of like what the UE receives?
I'm kind of doing a comparison, like here's direct path, and now what if I did a relay instead? So I'm basically trying to do a trade-off to figure out what the architecture, which architecture saves the most energy in a deployment. So it's a trade-off, it's a comparison between one architecture, fixed, and another architecture with a relay. So I'm trying to figure out which architecture is more energy efficient, trying to motivate us to start thinking about how we design our mobile and fixed networks for minimum energy.
So the reason I ask that is because, like, if the UE receives from both the base station and the relay at the same time, like that, those regions might change.
Correct. I'm not considering, I mean, the math will support the idea of simultaneous multi-transmitter or relay and direct transmitting at the same time. This is not done in the paper. What I'm trying to do is simply show there's an analytical tool to figure out which choice would be better. But you could take it further and look at what happens when both happen. In fact, we published at Globecom in South Africa in 2024 a remarkable paper that shows how you can use multi-user transmitter, multi-receivers, and use waste factor to figure out how a diversity or multi-user, if you will, multi-user MIMO system works and how to analyze that.
Yeah, thank you.
You're welcome. Thank you for the question.
I think we can take one more question. Right here.
Thank you for the talk. I was just wondering, what do you consider when you're trying to develop a new metric, maybe not necessarily with regards to waste, but in general? How do you go about that?
Yeah, how do I go about deciding a new metric? It's a good question. You know, I believe our role as professors and researchers are to be entrepreneurs. Entrepreneurs, my definition of an entrepreneur is you take a poor performing asset and bring it to a much higher value. And when you look at industry or look at how things are being done, if you're aware of how things can be improved, if you can jump in and make an improvement, that's I think valuable. I think that's our role as researchers, to figure out new ways, to explore new ways. We don't ever know if they're going to work or not. But I've always been motivated by trying to figure out a way to unify a lot of disparate inputs and information and try to compact it to the essence, because that makes us more efficient. That's being an entrepreneur. Right now in the 3GPP global standards body and the channel modeling work, from what I see, different companies show up, they present their measurements, they don't share the data, they don't have a common format by which they present their data, and they take 2.5 years to come up with a channel model, which is developed by committee, not based on any of the measurements, and there's no real basis. And then they use a model that has 3 random parameters, alpha, beta, and gamma, which are optimized and have no real relevance to the real world. If you look at the 3GPP channel model, alpha, beta, gamma, these are 3 coefficients used to match, and there's really no real world physical basis, yet radio propagation is real world. So I went to the standards body and tried to convince them that if you use a simple path loss exponent, it's less parameters, it's very simple to use, it's based on physics, and it's accurate. It's not quite as accurate. It gives up a 0.1 or 0.2 dB in standard deviation, but that's a fair price to pay if everyone's standardized. Well, industry doesn't like that so much, but they did do it for line of sight. So we were able to change the standard, and I think we were an entrepreneur in that, because now it's a much more efficient model. I realized back, well, I've been thinking about this for decades, and if you read Shannon's papers, and I like to read Shannon and Freeze every 7 to 10 years, I will read the papers on the beach. Go look at Harold Free's 2 papers from the 1940s. One is free space path loss transmission, and one is noise in receivers. And if you read Shannon's 2 key papers, one he did with Weaver, one he did alone, on the development of information theory, you see so much physical basis Shannon and Fries went back to Boltzmann, went back to the nature of molecules, went back to the fundamentals of when we didn't even have the atom fully discovered yet. And Boltzmann had this idea that, molecules have different states and materials change in different states. And you see Bell Labs following that footprint 50 years later, going back to fundamentals. And that's why their work is fundamentally used now, because they were based on fundamentals. So when I looked at energy back in 2008, 2009, I knew we'd someday have, I didn't know it'd be AI, I didn't know it'd be called that, but you knew computing would continue to scale with Moore's law. I realized then there was no fundamental metric for energy consumption and communications. So this has been a 15-year journey with many grad students, but I felt a need for all of us to be able to speak on the same page to be more efficient in our designs. So I think you look for opportunities to add value, to bring low-performing assets or waste and make it less wasteful. So in my mind, that's our job as researchers, to try to find problems that could have an impact and help the community. That's a nice question. I've never been asked that. I've never really thought about it. Thank you. Thank you all very much. I appreciate being here. Keep up the great work and enjoy this great new building. Thank you.